Ladies and gentlemen, thank you very much for your participation today, despite your busy schedules. We also would like to thank online audience for taking the time out of your busy schedules today. The 18th JAEA Annual Symposium is now open. I am Hanae Tsuji of the Japan Atomic Energy Agency, and I will be serving as an MC today. It is a great pleasure to meet you all. Today's program will last until 4:30 p.m. with a 40-minute break in the middle. I hope you will stay with us until the end. First of all, I'd like to introduce the distinguished guests who are present on site today. We wish we could introduce all the participants, but as representatives, we are pleased to introduce the members of the Parliament. Honorable Minister of the House of Representatives, State Minister of Digital Affairs and State Minister of the Cabinet Office, Mr. Akimasa Ishikawa. Honorable Member of the House of Representatives, Mr. Nobuyuki Fukushima. Honorable Member of the House of the Representatives, Mr. Satoshi Asano. Honorable Member of the House of Councillors, Mr. Kiyoshi Ejima. I once again express our profound gratitude for the distinguished guests to attend today's meeting despite your busy schedules. We have also received a congratulatory telegram, and I would like to introduce only the name. Honorable Member of the House of the Representatives, Ms. Asako Omi. Thank you very much. Let me call upon Masanori Koguchi, President of the Japan Atomic Energy Agency, as a keynote speech to report JAEA's vision exploration of a new future with the synergy of nuclear and renewable. Ladies and gentlemen, thank you very much for taking time out of your busy schedules to attend the 18th JAEA Annual Symposium hosted by the Japan Atomic Energy Agency. I am Koguchi, President of JAEA. I would like to say a few words upon the opening of the meeting. As you are all aware, last fall, the Kishida Cabinet announced a major policy, the so-called GX policy, to realize a decarbonized society by 2050. The policy calls for the maximum utilization of nuclear energy as well as the renewable energy. As a JAEA in a position to realize the Japanese government's nuclear energy policy through nuclear energy research and development, we have adopted a new vision, exploration of a new future with the synergy of nuclear and renewable in April of this year, and all of our staffs are united in our renewed efforts to meet the expectations. Today's annual symposium is entitled Toward a Hydrogen Society and will specifically report on the status of research and development on the utilization of the hydrogen with nuclear power. But before that, I'd like to talk about the major management policies of JAEA. I would like to begin my presentation. This is a summary of my thoughts as president of JAEA on how we should move forward as an organization in response to the vision, exploration of a new future with the synergy of nuclear and renewable. As you are all aware, nuclear energy is a topic that concerns the very state of our nation. Therefore, I'd like to raise the perspective a bit higher and to start from how we should respond to the big changes surrounding our country. First, there is the great waves of change surrounding our country. Politically speaking, the central concept of our country's diplomacy has been UN-centrism. As you are aware, the United Nations has been dysfunctional in the wake of Russia's invasion of Ukraine. In addition, economically, the free trade system, which was the premise of Japan's industrialization policy, is collapsing, and there are signs of a trend toward forming trade blocs. In addition, the rapid shift from a conventional carbon-consuming society to a decarbonized or a sustainable society has become a real issue for the society. These major changes in the political, economic, and social spheres are concurrently and rapidly appearing before our eyes. On the other hand, we have to take a bit of a critical review of how we, Japan, are going to respond. For example, Japan has an extremely low food self-sufficiency rate. It is concerned that food self-sufficiency ratio will worsen due to a decrease in population engaged in the primary industry or due to the aging. With regard to energy self-efficiency, we are, of course, in a poor condition compared to other G7 countries or many other large developed countries. In addition, the competition for energy sources in the world will intensify, and the cost will also rise partly due to the currency exchange rate problems. Then, the situation in Japan, which is deteriorating, as is represented by the so-called declining birth rate and aging population. So as the other items in the country's basic balance sheet, such as demographic and social infrastructure and social system. Therefore, there is a concern that there will not be sufficient capacity for new investment or that people's ability to pay taxes that could be reduced in the future. The international situation is becoming increasingly complex, as I mentioned earlier. On the other hand, I believe that Japanese people's mindset was becoming a bit inward-looking during the last 30 years. Let me put that in concrete numbers for you. The food self-sufficiency rate is 38%, energy self-sufficiency rate is 13%. Both of these figures are much lower than the among the G7 countries. As for the current situation in Japan, I apologize for the busy slide, but Japan's GDP has hardly increased over the past 20 years from 2005 and to 23. On the other hand, the United States has doubled in size and China has grown by a factor of 8. Yen is now valued at 150 yen to a dollar, which is significantly lower than its previous value of around 100 yen to the dollar. On the right is an interesting table. It shows the relationship between our national debt and GDP. If a country is growing even though the country is in debt, this red line will remain flat. However, this line is rapidly rising. A large data is available since year 1890. In the 70 years leading up to the Pacific War, which is compared with the 70 years after the Pacific War, are, oddly enough, along the similar curve. Also, the status of the energy mix is, this is a bit small, but you may not be able to see it. But in 2010, non-carbonized ratio, such as a sum of the renewable energy plus nuclear, was 34%. But in recent years, nuclear power operations have dropped, bringing the figure only to 28%. In fact, the situation was worsened. Therefore, the ratio of the thermal power in the middle, especially coal and gas-fired power, is increasing. As I mentioned earlier, Japan depends on foreign countries for its energy sources, and the electricity prices are also going right up. Under such circumstances, the GX policy is being presented by the government. How to understand this GX policy in the eyes of JAEA? Our policy is to create a low-resource but efficient society. Currently, we are rather high-resource dependent and low efficiency, yet we are sanctioned to turn around this. This is the way to clarify and strengthen Japan's position in the world. This is how I understand the GX policy. Under these circumstances, electricity rates in Japan are becoming higher, as I just showed you in the chart. And why is it so expensive? Generally speaking, it is the soaring prices of energy such as oil, gas, and coal. It is said that it is due to the international competition and the weaker yen. But is this really true? And on the other hand, I still see another problem, particularly in the low utilization rate of the power facilities. Renewable energy basically has a low utilization rate subject to natural conditions. On the other hand, coal gas power generation, which is used as a backup power sources, may have been affected by this problem and is a state of a low utilization. There are many nuclear plants that have been shut down or decommissioning is already decided, and only a few of them are in operation. Unfortunately, coal-fired thermal power plants have been restricted to a low operation rate due to CO2 emission restrictions. In other words, in total, the low utilization rate of each sector of power generation leads to high energy costs. This is borne by the people and the industry. This is my own analysis. So, as to what direction will this be resolved? One broad direction is, as I mentioned earlier in the energy mix discussion, right now we have 1 plus 1 plus 1 equals 2, 3. 1 plus 1 equals 2, which is such in summation or adds up of something like this. But the question is whether this can be extended to 1 plus 1 equals to not just 2 but 3 or even 4 by pursuing synergies with each other. For example, could it be possible by making good use of underutilized assets like uranium, depleted uranium, or sites where decommissioning has already been decided, to produce uranium batteries to store the renewable energy and then feed it back to the grid in a way well controlled by the power companies. This would increase the utilization rate of the installed capacity of the electric power companies. And I am also wondering if it is possible to decarbonize industrial parks and zones by successfully using the high-temperature gas-cooled reactors as energy centers, and by using renewable energy to compensate for the shortfalls, which we will report to you today later. By combining these two technologies with renewable energy, we can create a synergetic effects, which will be bigger impact than simply adding them together. The second direction is to aim for securing a long-term stable energy source while meeting the new demands of building a deoxygenated society, or convert the radiation or heat that comes out of it directly into energy. Through this kind of research and development, we believe that this could be a direction for a solution. Furthermore, we do not yet fully understand the characteristics of nuclear power. Therefore, our current focus is on power generation. Can we utilize nuclear energy in various industrial fields such as medicine, materials, agriculture, etc.? Can we achieve this with high efficiency and lower resources? These major directions can be summarized as follows. First, pursuit of synergistic effects of different energy. Second, being sustainable in a sense that it can be used as a synergetic, long-term, stable energy sources. The third, ubiquitous in the sense that it can be used in a variety of fields. This is one of the major targets of JAEA that should work on going forward. Let me further elaborate. For example, in regards to synergies, one of the major concerns of the public about nuclear power, on top of the pursuit of safety and efficiency of the nuclear reactor itself, is an R&D in making nuclear power more sustainable, aimed at optimizing Japan's energy generation and coordinating with renewable energy. Research and development that reassure the public by solving back-end problems and demonstrating the safety of nuclear power in general. Ubiquitous diversification of nuclear energy refers to research and development aimed at maximizing the potential of nuclear energy and promoting its application in a variety of fields. This is the schematics of what I have described. Synergy, sustainability, ubiquitous are well combined, and we would like to work on research and development in these areas. For example, the development of high-temperature gas-cooled reactors, which we are presenting to you today, involves both synergy and ubiquitous. And this is a combination of using HDGR to successfully combine hydrogen with renewable energy to improve efficiency and to utilize the various effects produced by HDGR in other areas as well. I also believe that in order for our country to build the position and society that the GX policy advocates, it is very demanding to pay for everything with taxpayers' money. Therefore, I believe that at some point, a stage will surely come when private funds will be utilized and private sector vitality are going to be harnessed. However, nuclear power is a very risky business. I believe that analysis shows that there are three layers of the risks. First is technology risks, second social risks, and the third is government risk, which is the national policy or regulation risk. First, we need to lower the technology risks. And this is exactly the basis of what we as a research institute should be doing. By reducing technology risks, we reduce risk in various social and sociological issues involving social acceptance or finance. And in such a situation, the government's policy and regulation will reduce in accordance with the reduction of the technological risks. I think that the private sector, to a large extent, will provide technical assistance when the risk comes down to a level where the risk makes sense to a business to some extent. Therefore, during the high-risk stage, we'd like to join forces with all the stakeholders and try to work on to reduce the risks. Let me convert this to value. The value of social activities of such as nuclear power is recognized to be very low now. This is not so strange considering the Fukushima Daiichi nuclear power plant accident. As I mentioned earlier, looking at the global situation and the domestic situation, I think we need to value this somehow. By lowering the risks, the potential value will become visible, and at the same time, in a sense, reproduction and recirculation of new value may be created. In other words, I think that GX policy is not only to make visible the value of the current potential of the nuclear power, but also to be directly connected to the growth areas and the new capitalisms that the Kishida cabinet is currently pursuing. We have to think carefully about when to shift from public sector initiative to a private sector initiatives. However, in the big picture, we should start thinking about this somehow. On the other hand, we must not forget that we must solve the problem that nuclear power possesses. Nuclear power cannot be promoted without solving problems. What are the problems that nuclear energy faces? One concern is about the safety, particularly after the accident at the Fukushima Daiichi nuclear power plant. Some people are still concerned about the possibility of natural disaster or human error resulting in the failure of controlling nuclear power well and causing a serious disaster. We have not clarified even a rough sketch of decommissioning or recovery from accident, of not just of a plant suffered from the accident, but also for a normal plant. We have not defined a process of shutdown and decommissioning and so on. The public does not yet have a firm understanding of the levels of radiation exposure effects. On the other hand, Russia's invasion of Ukraine highlighted the story of Zaporizhzhia nuclear power plant. The public is concerned about the safety of nuclear facilities against the war and the terrorists' attack. I believe that the public is concerned about the safety from wide-ranging safety considerations. Another concern is about radioactive wastes. Japan has a lot of nuclear materials with a long half-life period due to light water reactor power generators. The policy is to vitrify these materials and bury them underground. But as you are well aware of, progress has been very slow. The disposal of medium and low-level radioactive waste generated by nuclear experiments facilities is also undetermined. Furthermore, there is the issue of trade amounts of radioactive materials. Tritium, in particular, released into the atmosphere and oceans. Under these circumstances, JAEA would like to promote research and development in a direction that solves these problems. As for the safety of the nuclear facility, we will promote research and development on new reactors with high safety features and to improve accident resistance of existing facilities. These are our research facility written in red. In addition, we have a lot of works in decommissioning of the reactor. Accumulating this knowledge and working towards safe and efficient decommissioning, in particular identifying decommissioning pathways of the Fukushima Daiichi accident plant, is a major issue. To this end, we are actively working on mainly in Fukushima division. We would like to also provide appropriate information on the effects of radiation exposure on human body. However, with regards to the major issue of terrorist attack and war, although JAEA participates in international nuclear non-proliferation and nuclear security groups, we honestly believe that this is a very difficult area for JAEA to deal with. Then there is a question of what to do with radioactive waste. This is known as nuclear waste, but we'd like to promote this kind of research to see if we can somehow turn it into nuclear resources. This is to extract rare metals from this waste and recycle and utilize them later, or using neutrons to change it into a substance with a short half-life. This is the kind of research that we are conducting. Through this kind of research and development, we will deepen the public understanding of nuclear energy, reduce social and technological risks, and at the same time, reduce social risks so that nuclear energy can be used as a predominantly stable energy resources in our country. And we'd like to promote research and development in this direction. In summary, Professor Claudia Golden of the Harvard University, the laureate of this year's Nobel Prize in Economics, said something interesting. I read her book over 20 years ago and examined technologies such as the radio, the automobile, and the computer revolutionized the society, and her analysis says that all of them took more than 70 years from their first invention to their practical application and broad penetration. And in such process, there's always negative aspects as well as positive aspects as well. They all solved the problem and advanced to the higher penetration. The spread of automobiles, for example, is naturally convenient, but as it becomes more spread, there are problems of exhaust gas and traffic accidents. By solving these technical problems, and also it is extremely important to solve the problem of carbon dioxide emissions through the use of electric vehicles and variety of technologies. All of them are very important for the wide use of vehicles. The same applies to nuclear power. There are many ways to define what makes nuclear power practical. If the atomic bomb, which is a very unfortunate, is put into practical use, it was about 70 years since then. But we do not yet fully understand the potential of the nuclear power. We are already inexperienced in technology and means to control. However, the energy produced from nuclear reactions, nuclear power, is very foundation of our universe. Radiation from nuclides are very common things. We, humankind, choose to separate from carbon-consuming society and transform toward decarbonized society nowadays. With this background, in this era and time, we at JAEA are committed to further the research and development for the creation of a new society using the nuclear energy. This concludes my presentation, and thank you very much for your kind attention. Thank you very much for your kind attention. We are very pleased to introduce here several members of the Parliament who arrived later. Honorable Member of the House of Representatives, Mr. Shunsuke Mutai. Honorable Member of the House of Councillors, Mr. Hirofumi Takinami. Honorable Member of the House of Councillors, Mr. Yoshihiro Kawano. We will now take a break for about 40 minutes, and we will resume at 3:27 p.m. It is time to resume, and we will take questions after two reports are presented by JAEA. The first speaker is Dr. Narayaki Sakaba, Director of HTGR Project Management Office, will give a presentation titled Contribution Toward Hydrogen Society, Achieving Carbon Neutrality by HTGR with Inherent Safe Characteristics. I am Sakaba with HTGR Project Manager Office. Let me report on the viewpoint of how can HTGR work toward the coming hydrogen society. First, I will introduce the contents of today's presentation, requirements for hydrogen supply sources in a hydrogen society, next on features and current status of HTGR, carbon-free energy sources, finally on challenges and responses for social implementation of HTGR. I'd like to discuss in this order. First, the requirements for hydrogen supply sources in a hydrogen society. I'd like to give a brief overview, and I will just simply cover, because it was covered extensively by Dr. Kato's presentation. There are three parts. First of all, in terms of domestic hydrogen production, there is a large supply of liquefied hydrogen transported in large quantities from overseas. But as is mentioned by Dr. Kato, there is a considerable advantage in producing hydrogen domestically. At the present time, overseas hydrogen requires mass transportation of a liquefied hydrogen, and the cost is high at 160 yen per cubic meters. Second point, large and stable hydrogen production is necessary. Economical production industrial processes need to be a long-term and continuous. For this purpose, assuming carbon neutrality, a large amount of hydrogen is needed. At present, Japan uses 2 million tons of hydrogen, and it is estimated that 20 million tons or more will be used by year 2050. Third, the hydrogen produced must be carbon-free. The development of technologies to make industrial processes carbon neutral by the use of hydrogen will intensify in the future. In particular, competition with the foreign countries had to be considered, such as carbon pricing and etc. Currently, Japan has a carbon tax of about 300 yen. In the future, this tax will be 32,500 yen, and in fact, in Europe, it has already exceeded 10,000 yen. Therefore, we can imagine that the coming hydrogen society will have a completely different value system than the current society. Based on these premises, I will now outline HTGR developed by JAEA. First of all, what is our HTGR? There are two main characteristics. The first is it has excellent safety features. Second is it can be used as a diverse range of heat application. In terms of superior safety, we will be able to design a reactor that does not cause core meltdowns due to its inherent safety characteristics. As for versatilities in heat applications, as the name speaks itself, HTGR supplies high-temperature heat above 900 degrees Celsius, which can be provided in many applications. For example, one unit of HTGR with a thermal capacity of 250 megawatt per unit is estimated to supply hydrogen for about 300,000 fuel cell vehicles. We will discuss these two advantages in more detail on the next page. The first is superior safety. The superior safety of HTGR is derived from three key factors. First is ceramic-coated fuel. We use fuel particles coated multiple times by ceramics. The fuel particles start to break down when the temperature exceeds 2,000 degrees Celsius, and therefore, in any case, the fuel will not break down unless the temperature exceeds 2,000 degrees Celsius. Next is graphite structural materials. Graphite has a high heat capacity for HTGRs, which suppresses output density low. It is also an excellent heat conductor and thus has excellent heat dissipation performance. Therefore, even if heat is generated in an accident, reactor has an excellent ability to store a certain amount of heat. The third is coolant used in helium gas. Helium gas is extremely stable, does not change the fates, and does not react chemically. Therefore, even at a high temperature, there is no phase change and the helium gas remains as gas. The high temperature gas itself has the property naturally stop rising, cooling, and trapping radioactive materials even if the power source and the coolant are lost. Next is about the versatility in application. How can the heat from HTGR be used? The chart on the right shows that the heat above 900 degrees Celsius at its peak is used for hydrogen splitting from the water, and the heat below 900 degrees downstream are used for gas turbine power generation, and if the temperature is even lower, the heat is used for hydrogen production, oil refining from natural gas. The heat at the lower levels can be used for district heating and desalination needed in the Middle East and elsewhere. The main point is that this green and versatile energy supply can contribute to decarbonization and emissions reduction in the areas other than power generation. In Japan, we have HCTR in Orai-cho, Ibaraki Prefecture, which is used for testing and research. This HTTR is our country's first HTGR and is currently owned only by China and Japan in the world. China adopted the pebble bed module. Japan is the only country using pin-in-block type reactor. Nuclear reactor thermal output at 30,000 kilowatt and helium gas is used as a coolant. The core structural material is graphite. R&D began in 1960s and the first criticality was achieved in 1998 and the successful completion of 50 days of continuous operation at 950 degrees was achieved in 2010. The plant was then restarted in July 21 after complying with all new regulatory standards. This HTTR was the first in the world to achieve the temperature of 950 degrees Celsius in 2004, and the chart itself shows the output temperature trend at the time, and this is still the highest record in the world. Thus, we have attained a significant achievement such that how we can utilize this high temperature for the development of future demonstration reactors and how we can utilize them with a technological advantage. Thus, HCTR itself can be built using Japan's technologies alone. HTTR was designed and built by all major Japanese heavy industries, including Toshiba IHI, Hitachi Fuji Electric, Kawasaki Heavy Industries, with Mitsubishi Heavy Industries as the lead manager. As for the high-temperature materials, Hastelloy XR was developed jointly by Mitsubishi Materials and then JAERI, JAERI at that time. In the area of fuel, the world's best performing fuel is owned by NFI, Nuclear Fuel Industries. In addition, Toyo Tanso has the capacity to produce nuclear-grade graphite IG-110, which is a coating material for the reactor core. This graphite made by Toyo Tanso is also used in HTGR in China. In this way, it is possible to construct HTGR's demonstration reactors using only domestic technologies alone. Before March 11th disaster in 2011, we conducted a safety demonstration test using the HTTR at the HTTR located in Oraimachi. The schematics are shown on the left. This shows the cross-section of the core. The core is cooled by helium gas flowing through a gas circulator, and control rods are placed at the top of the core, and when the reactor shutdown starts, the control rods are descended in this area. In this test, we conducted an experiment that the helium gas flow in the gas circulator was stopped while the fuel control rods were not inserted. The chart on the right shows the result. The red line is the measured value and the blue line is the simulation. The upper line is the reactor power value and the lower line is the average fuel temperature. Horizontal axis elapsed time, while the vertical axis is the temperature at the bottom and the reactor power at the top. At the time 0, the flow rate of the gas circulator is set to 0. The nuclear power output then drops quickly, while the fuel temperature rises temporarily, but then drops and returns to the natural state. All of these phenomena proceeded only by the law of the physics and without interruptions. This is what is called the inherent safety of HDGR. If you build a too large reactor, these phenomena will not occur. Therefore, in order to take advantage of the safety features of HDGR, they have to be small. Then the output is inevitably limited. But this is a trade-off. But a certain size, HDGR has its inherent safety characters. These are the characteristics of HDGR, and in the National Basic Policy for Realization of GX, it is listed as one of the 5 types that should be developed in the future. The area shown in green is HDGR. The basic design is scheduled to start in this fiscal year. The operation is scheduled to begin in the late 2030s, and it has been decided that MHI will be responsible for the core function of the basic design. As for the budget, as stated in the lower left corner, it is proceeded as a part of the national government budget. As for the issues and measures to be taken for the future social implementation of the HDGR, as I explained earlier by our president, we believe that the issues can be broadly divided into social, technical, and policies. I will omit the policy part from today's presentation, but I believe that it will take time for the regulations to be implemented. But the first is society, which requires the site selection and the development of business scheme. Specifically, we are planning to build a business model that can win social acceptance. In this sense, we are currently planning to use a project to reach out to stakeholders and, as I explained on the next slide, to take advantage of the national UK government's project. Next is about technology. We believe that this is the task of JAEA, but first of all, we must establish reactor technology. And in demonstration reactor, we would like to apply the HCTR technology so that there will be as little technological development as possible. However, several issues arise when the reactor beginning larger. One is the configuration of the cores. One R&D element is whether to use a large angular core or not. In addition, we need to develop facilities larger and more sophisticated and establish reprocessing technology for the fuel. Reprocessing is a question that we are often asked about by the public. As I mentioned earlier, HDGR is solidly encapsulated with ceramic, and we have done some R&D with new fuel and applied physical damages and chemical extraction, but we have never tested with a reprocessed fuels. The challenge is to verify the technology on the reprocessed fuels. The other challenges is the standard and specifications. We are currently developing safety standards and structural standards, and these are in progress, but the safety standards should not be defined by the conventional light water reactors alone. But we need to specify safety issues unique to HDGR so that we can enjoy advantages. Development of heat application technology is also important, particularly for coupling. There's no chemical plants adjacent to the nuclear plant in the world, so technology has to be established. And the last is the hydrogen production technology. This is eventually have to be carbon-free technology, and we are currently discussing what is the best technology for this purpose. We need to solve these challenges through the development of domestic demonstration reactors and the HTTR and heat application test. HTTR heat application test project itself. Well, existing HTTR is here, and we are planning to couple with hydrogen generation plant via steam reformer right next to it. specifically, we will install secondary piping for HTTR and use the heat from the secondary system to make hydrogen. The steam reformer itself produces carbon dioxide, but for which there is already an established technology. We would like to connect hydrogen plant and steam reformer first. As a next step, we would like to consider carbon-free. That is what we are thinking at this moment. This is the schedule. We started last year as part of the Green Growth Strategy. We hope to apply for a permit for installation by the end of the next fiscal year. Our current plan is to achieve hydrogen production at around 2028. By achieving this as soon as possible, we'd like to further establish this technology ahead of the rest of the world and introduce this technology in the British project, which I will elaborate later. There are several applicable hydrogen production technologies. There are 4 at the bottom. Further left is methane reforming. It gives off carbon dioxide. The 3 on the right are green hydrogen, which does not emit carbon dioxide. The 3 on the right, from the left to the right, are using high-temperature steam electrolysis, SOEC, which is partly commercialized. Then in the middle is methane pyrolysis. Methane is differentiated and extracted as solid carbon and hydrogen extracted. The rightmost is IS method, which is a thermochemical method to make hydrogen using circulation of iodine, sulfur, water, and oxygen. We are developing such technologies. Well, we consider these 3 candidates, and we will assess the maturity level of technology and evaluate what will be the most appropriate for the early achievement of FTGR, and we are currently conducting FS. It is not just potential, but we need to think about social implementation. We need to think about the earliest commercialization, and from this perspective, probably current SOEC may have a reasonable advantage. Next is social implementation model of HTTR. In the field of social implementation, we can build, for example, an HTTR in an industrial complex, or HTTR in an energy supply center, for example, and by flowing helium gas, heat can be used from various aspects and further utilized for hydrogen, electricity, and steam. And we'd like to supply these byproducts to oil refineries, petrochemical plants, chemical plants, and steel mills. Also, hydrogen, electricity, steam have capacity to adjust power, so we would like to use for curtailment of renewable energy, as Dr. Kato mentioned earlier in his presentation. For example, HTGR can be used to produce hydrogen during the day and used to produce electricity at night. Also, it can serve external demand. Hydrogen, electricity, and steam can be used to meet the demand flexibly in the neighborhood. However, HTGR's greatest strength is in the utilization of the heat. So we are thinking about we can create and use hydrogen steam in the industrial complex without losses. To put it other words, we can provide new social value. I believe that HTTR can be used to achieve carbon neutrality in industry and to strengthen the resilience of carbon-neutral society and its systems. From here on, I'd like to touch upon the United Kingdom, who is also trying to utilize HTGR in a similar perspective as Japan. UK decided to specialize in HTTRs as the next generation reactors. The power generation will be done by SMR, and in UK, SMR in UK is light water reactor, but HTTR will be used for the parts that uses heat, especially for the plant that is difficult to reduce CO2 emission. With this in mind, UK is proceeding with the HTTR demonstration program, and program is comprised of Phase A, B, C, and Phase A is a pre-FEED study which has already been completed. Phase B and Phase C follows, and Phase B is currently underway. Phase A For Phase A, 4 institutions have applied. Phase B is now underway with 2 shortlisted institutions. NNL, a British National Research Institute, and JAEA have teamed up to apply for Phase B, which has been adopted. The other institution is an American company. In order to promote this program, especially for decarbonization in UK, a comprehensive memorandum of understanding on HTGRs was recently signed between NNL of UK and JAEA President in September. This is a signing ceremony held in the presence of Minister of METI, Mr. Nishimura, and Ms. Curtijo, Secretary of UK Designate. Upon signing, we will proceed with the practical application of HTTR in UK. One big difference from Japan is that UK has already a candidate site. This is a brochure prepared by EDF Energy. It's a bit difficult to read. But here is a map of UK describing the site already approved. And there's a site called Hartlepool located in the northeast of England. And AGR is currently in operation. And AGR itself is scheduled to shut down in 2026. EDF Energy has conducted a Phase A FS studies. And as I mentioned earlier, they are planning to build an HTTR next to AGR. The reason is that the neighborhood town is called Tees Valley. This is the site of the largest industrial complex in UK. Chemical plants, steel mills are located in this area, and there is already a supply networks and there are invisible infrastructure available behind the scene. So this plan will be able to use such infrastructure and provide the heat from HTGR so that it can contribute to carbon neutrality. So this is the specific model. UK uses renewable energy, but in the case of UK, wind power from North Sea accounts for a very large proportion. On the other hand, we have heard that the demand for the heat in Tees Valley is expected to be 4 gigawatts by 2030. Of this 4 gigawatts, 3 gigawatts will be coming from blue hydrogen, or a combination of fossil fuel and CCUS. In addition, as a green hydrogen, they will be using renewable energy, especially using wind power from North Sea. We heard that this already been secured for 3 gigawatts. So they are expecting HTTR to provide remaining 1 gigawatt. So in the future, we will probably build a demonstration reactor here in UK, and we will use this site as the first candidate. This is the plan that is underway. JAEA is cooperating this project. The HTGR itself will be built with Japanese technology. The UK operating carbon dioxide cooled reactors, but almost no HTGR. We are in the process of introducing our technology, and we would like to eventually bring back such technologies to Japan. In addition, we will need to locate in a close proximity to Yurzu's site in the future. This is the Hartlepool site, Tees Valley site, as I mentioned earlier. And I wrote here, this is the potential HTGR site. Blow-up map is on this slide. In the section, for example, the emergency plan for the large light water reactor, where it says roughly 10 miles. But US NRC's assessment is about 16 kilometers in this dotted line. There is an idea of thinking about how to fit in within this dotted line. But another concept is to utilize this blue line. Blue line, which is a 400-meter HTGR energy evacuation zone that X Energy, a US HTGR company, has already mentioned in the discussion with the NRC. I hope this can be also realized in the future. So if this is feasible and we can have a close proximity to the users. Furthermore, the residents living near the Hartlepool, Tees Valley, site are quite aware of the benefits of nuclear power plant, and I have heard that survey shows that 70 to 80% of the residents are in favor of nuclear power plant. I believe that achieving this location near the place of the demand users area will be a major step in the future development of HTGR. So this is the summary of global HTGR development. So first of all, these four countries are promoting HTGR markets. US Development of Energy, DOE, has a plan to support the development of innovative reactors, especially X-Energy Company has a small electricity output of 750 degrees Celsius, but there's a plan. In UK, as I mentioned earlier, DESMADS is supporting the development of a small HTGR module to start operation in the early 2030s. It is indeed a challenging schedule, but that is how it is proceeded now. We have also received a contract research project from Poland, which is not included in today's presentation, but Poland is a country that uses a lot of coal, and our major goal is to supply steam with HTGR by replacing coal. In fact, Poland has a plan to build a research reactor first, and then a commercial reactor. With regard to the research reactor, JAEA's local office is contracted with half of the Poland's budget in this regard and provide the design information. Lastly, this is China. China is the most advanced country in this regard. Unfortunately, we are behind them. A demonstration reactor is already in operation with transmission starting in 2021, and full power operation was achieved in 2022. Based on the successful operation of the demonstration reactor, we believe that China will probably announce the construction of a commercial reactor in the near future. I have heard that contracts for HTGR commercial reactors have already been completed with 6 municipalities. As you see, HTGR around the world is accelerating. On the other hand, as you can see, the countries other than Japan are using HTGR with an upper limit of 750 degrees Celsius. Japan is the only country that has achieved a high temperature of 950 Celsius degree. We'd like to take a full advantage of this and expand our technology to the world so that we can continue to be the world leader in this field. In closing, let me summarize. In terms of hydrogen production in Japan, there are several issues. We are looking into the location of HTGR with an excellent safety features in close proximity to users' premise in Japan as well. UK already started the planning, and we are hoping to achieve this in Japan through the dialogue with the regulatory side and try to realize in the demonstration reactor. Second, massive and stable production of hydrogen in supplying heat at the temperature exceeding 900 degrees Celsius by HTGR. Japan already have this technology. And thirdly, we would like to supply hydrogen in a completely clean environment by building a carbon-free hydrogen production facility near HTGR. The first and the foremost priority is to establish a technology to couple the HTGR with the calorimetric test equipment and hydrogen production equipment. And second, this is the development of the demonstration reactor, which also aims to start operation in the second half of the fiscal year 2030, while also being able to supply the necessary amount to become carbon neutral by 2050. I would like to work with a great sense of speed, and I'd like to work with the industry to achieve our country's goal of zero carbon emissions by 2050 with all of our efforts in JAEA. With this, I'd like to conclude my presentation. Thank you very much. Thank you very much for your kind attention. We are pleased to introduce the Member of the Parliament in attendance here, Honorable Member of the House of Representatives, Ms. Asako Komi. Next report is titled Technological Innovations to Transform Radioactive Waste into Resources, the Key to a Sustainable Nuclear Energy Utilization. Let me call upon Dr. Takanori Sugawara, Principal Researcher of Nuclear Science and Engineering Center of Nuclear Science Research Sector, for his presentation.
My name is Sugawara. I belong to Nuclear Science and Engineering Center. The topic is technological innovations to change radioactive waste into resources, so it is a bit different from hydrogen. But it's appreciated if you could stay with me until the end. Thank you for your cooperation. Today, I believe that our President mentioned 3 pillars of R&D in JAEA, as indicated on the slide. 1. Synergy of nuclear and renewable. 2. Make nuclear power itself sustainable. 3. Diversification of nuclear energy utilization, ubiquitous. As my theme is technologies to change radioactive waste into resources, I would like to introduce the 3 R&D activities. The first is usage of depleted uranium for storage battery, which is related to synergy and ubiquitousness of multi-purpose usage. Second is utilization of elements in spent fuel, which is related to sustainability. The third is power generation by heat and radiation, which is also related to ubiquitousness. Let's talk about the first technology. I would like to share with you this number, 16,000 tons. Will you be able to tell what this number represents? It is amount of depleted uranium stored in Japan. As participants here today probably understand very well, new fuels used in nuclear power plants are called enriched uranium. Highly combustible uranium-235 inside natural uranium is collected and enriched to be used for power generation. And what remains after uranium-235 is removed, which is mainly composed of uranium-238. That is called depleted uranium. The depleted uranium is currently stored to be used for fast reactor in the future. As of 2021, around 16,000 tons of depleted uranium is stored. Against that backdrop, we are currently working on a research and development, thinking of possibility of using the depleted uranium as storage battery. In other words, we are thinking of storing surplus electricity from nuclear power plant and renewable energy inside this storage battery, making contribution to peak shift and grid stabilization, and sending the power to point of consumption. Furthermore, we are thinking of using this as an emergency power source at nuclear power plants as well. So our idea is to develop uranium-based redox flow battery to use non-burnable uranium as a resource to store surplus electricity generated by renewable energy and nuclear power plants. Let me explain the uranium redox flow battery. As shown in the diagram, there are two types of tanks, and uranium solution circulates in the tanks. As for the uranium, there are 4 different uranium valences as shown. In this system, that difference is used to charge and discharge at the cell. What are the features of the uranium redox flow battery? One feature is its large capacity. Basically, in this concept, you can increase amount of storage by increasing capacity of the tank. According to one estimate, 30,000 kilowatt-hour, which is equivalent to electricity used in one day by 3,000 households, can be stored by using 650 tons of uranium. If we are to convert 16,000 tons of depleted uranium, in other words, all the depleted uranium in Japan, into storage battery, it is estimated that it would be equivalent to 740,000 kilowatt-hour. That is 25 times the number shown here, meaning we can store electricity worth 75,000 households. Additionally, it is known that performance of the redox flow shows little or no degradation due to charging and discharging. Therefore, running cost is low. We can also use uranium, which can fully be procured within Japan, so it can be made semi-domestically. As I mentioned already, non-burnable uranium is simply stored at this moment, but we think this can be used effectively for electricity storage. Now, I suppose that many people wonder why we should use uranium. Here, I listed advantages and disadvantages of using uranium. The redox flow battery itself is a practically used technology, which is structured of vanadium. Though we are fully dependent on import for vanadium element. To address this point, we believe the depleted uranium can perhaps be used to make the semi-domestic battery. Another point is that it is more efficient than vanadium. Let me share an example. Electricity loss occurs all the time when we recharge. That loss is around 20% in case of vanadium, but loss is only 3% for uranium according to a report, making it efficient. On the other hand, one known disadvantage is instability of uranium valence when it is contaminated with water, though it has already been confirmed that it can be stabilized by electrolyte preparation. Furthermore, handling of uranium as nuclear fuel material can be a challenge. I would not say that it can be installed in a variety of locations, but, for example, we think it can possibly be used in the way shown on the slide and be installed in nuclear power plant sites. Here is current status and future prospects. Since a report on organic solvent-based uranium battery was made in 2007, reports on uranium redox flow battery are only published in Japan. In this fiscal year, we constructed a small-scale battery using uranium as active material and confirmed its operation. If this proof of principle is achieved, it would likely be the world's first achievement. We will conduct the proof of principle this year, and once that is confirmed, then we will design the actual battery in the next fiscal year. We look forward to developing a storage battery with about 100 grams of uranium in about 3 years, so it can gradually be scaled up. Let's move on to the next topic. Here, I am presenting this number, 30 billion yen. It is related to radioactive waste. As shown on the pie chart, there are a variety of elements inside the spent fuel, or in other words, inside nuclear fuel after being used at nuclear power station. About half of them is rare earth and platinum group metals. Please refer to the table on the platinum group metals. There are 3 PGMs, ruthenium, rhodium, and palladium. If reprocessing plant in Rokasho village of Aomori Prefecture is to operate and process 800 tons of spent fuel per annum, the elements with amount shown in the table can be secured according to an estimation. The amount is equivalent to around 30 billion yen in total. In other words, there is a possibility that we can utilize 30 billion yen worth of elements every year. Though our current idea is to have all the elements buried in the ground. And there are PGMs and rare earth inside the spent fuel, so it can be viewed as a precious resource. Furthermore, majority of the PGMs and rare earth are being imported from the overseas. If we can develop new supply sources, it can lead to ensuring of resource security. Therefore, the JAEA has been working on developing element separation technologies. By advancing the technology, utilizing existing facilities, and applying the technology to spent fuel, high-level liquid waste, and industrial waste known as urban mines, we look forward to developing practical separation and utilization technologies for useful elements. Let's look at the actual ways of separation. Allow me to introduce one of the ways called solvent extraction. As for the method, the JAEA has already been developing select process, shown in the slide. The process has been under development mainly for separating minor actinide called americium and curium. By using that process as a base, we are trying to develop a technology to separate elements such as palladium and rare earth, which I have mentioned. We think this initiative is effective in reducing the volume and hazard level of radioactive waste by combining with nuclear transmutation. Let me introduce you to another method called laser-assisted separation. We want to separate minor actinide called americium and curium from rare earth. But the minor actinide and the rare earth have chemical similarity, which makes it very challenging to separate them. Though here, for example, by applying laser at absorption wavelength against americium, we can cause laser-induced photochemical reaction with americium. We are currently developing a technology to selectively separate americium only by letting it either tie or not tie with liquid called extraction solvent. The technology has high element selectivity, so it is expected to simplify process and reduce secondary waste. A press release was already made on it by the JAEA last year. Here is current status and future prospects. Research on separating useful elements from spent fuel has been conducted already, but it is still in the basic research stage and has not yet reached stage of practical application. In the impact program conducted between 2014 to 2018, a similar research was conducted. It was confirmed that 95% of a PGM, palladium, can be recovered by a method called wet electrolysis, though that is also in basic research stage. On the other hand, our idea is to realize advancement of the separation process to extract valuable element from waste solutions, even if it may only be in a small amount. Furthermore, as I mentioned, we are thinking of possibility to apply such technology not only for radioactive waste but also for urban mine. So by extracting useful elements, we hope to extract several dozen grams of such elements from fuel solution in about 3 years and scaling the technology. This is the last item, 4.8 kilograms. This is related to space exploration. As you may know, the NASA has launched a Mars exploration rover called Perseverance. And Perseverance has 4.8 kilograms of plutonium-238 as a heat source. Here, you can see a conceptual diagram. The heat generation from plutonium-238 is converted to electricity, and the electricity is used to have the rover move around, explore, and send its data to the Earth. So, why is plutonium-238 is used? As I said before, elements used to convert heat to electricity are sensitive to radiation. On the other hand, plutonium-238 has high heat generation but has low radiation. So, this element is often being used for space exploration, especially by the US. On the other hand, for Japan to launch a rocket with this plutonium mounted seems quite challenging. Though, if we can utilize radiation-tolerant thermoelectric element, that could expand the options for isotopes as heat sources. Against that backdrop, currently, we are trying to use and convert heat and radiation from radioisotopes into electricity as much as possible. As written here, we are working on realizing semi-permanent, maintenance-free power supplies in harsh environments that are not easily accessible by humans. We are proceeding with research and development while thinking of using the waste itself as energy source to operate minimum equipment when power supply of nuclear power station is lost, or to monitor highly radioactive waste geologically disposed on top of its usage in space. As for conversion of heat into electricity, we are paying our attention to a technology called spintronics. This is a hybrid technology of electric and magnetics. I am sure everyone knows that electrons circulate around nucleus, and charge of the electrons make the electrons move, which causes current, the main player in electronics. On the other hand, the electrons are rotating as well, which is called spin current. The spin current is the origin of the magnetic current. The spintronics is a technology that tries to control and utilize the spin current. The technology itself is already in practical use as magnetic random access memory, as shown here. It is very energy efficient and has high radiation resistance, so the technology is used as memory element with such characteristics. We are thinking of using the spintronics to convert heat to electricity. Existing thermoelectric element system and spin thermoelectric element are compared on this page. The conventional thermoelectric element has those pebbly P and N-type semiconductor elements connected in series, and current is generated by temperature difference. This is already used in a variety of areas. The power is proportional to the number of the elements. On the other hand, because of semiconductors connected in series, when a portion is damaged, for example, when the semiconductor is damaged because of radiation, performance may deteriorate. On the other hand, the spin thermoelectric element is made of thin metal and magnetic material films pasted to each other. As shown in the photo, by causing temperature difference, spin current will be generated, which makes the current to flow in this direction. As it is made of metal and magnetic material, it has high radiation resistance. We actually confirmed integrity of the element by irradiating it with 1 megagray of gamma rays. Next is on power generation by radiation. On the left, you can see a diagram on photovoltaic power generation. When sunlight hits electrode, electrons inside N-type semiconductor will move, causing current. Gamma ray power generation is a system which sunlight from the PV is replaced by gamma ray. The principle itself is same as photovoltaic power generation. We have already demonstrated its principle by applying Harima's spring-8 synchrotron X-rays to an element made of Ni and SiC. The synchrotron X-ray is used as an alternative of gamma ray. Let's look at current status and future prospects. Proof of principle for both the spin thermoelectricity and the radiation power generation that I talked about are confirmed, though The issue is their low power generation efficiency. So, it is required to improve power generation efficiency and to conduct demonstration tests using radioactive waste. As part of power generation demonstration, which utilizes things such as RI, we pasted an element on primary cooling system piping of JRR3 located in the JAEA Nuclear Science Research Institute, as shown here, to conduct power generation tests in this fiscal year. In 2 years or so, we look forward to demonstrating power generation by using radioactive waste. Here's a summary. We promote research on the following technologies for converting radioactive waste into resources. First is using depleted uranium as storage battery to enjoy energy with renewable energy. Second is utilization of elements in spent fuel to realize resource security and make nuclear power sustainable. Third is power generation by heat and radiation for use in IoT and severe environment to make it ubiquitous. These 3 things can be referred to as seeds of innovations found in basic researches conducted by the JAEA. To have the technologies implemented in the society in the future, we want to grow the seeds. Though we believe that social implementation is a role that shall be played by cooperations and other research institutions. We have already started to grow the seeds, but we want to collaborate with a variety of people to proceed with research and development from this stage, so that eventually we can collaborate with a wide range of operators for research and development instead of doing everything on our own. I put what we would like to pursue in the end of my presentation. Here you can see concept of current nuclear fuel cycle. Our idea is to add new values to the nuclear fuel cycle by proceeding with technological innovation that I've introduced to you today. With this, I would like to conclude my presentation. Thank you for your attention. Thank you very much for your attention. We would like to take questions for the 2 presentations. The time is limited, therefore, please keep your questions concise. We will take 1 question from each person. It is appreciated if you could provide us with your name and your organization when you ask a question. Now, the audience in the venue with questions are kindly asked to raise your hand. Some questions are raised from online audience, so let me share one. What would be output of high-temperature gas-cooled demonstration reactor? What would be its budget? What about industrial reactor? I, Sakaba, will respond to the question. As for output level, as premise, we would like to do this as a continuation of HTTR and aim for what is viable in terms of economics and construction period, etc., and do this at a location where its safety can sufficiently be utilized. For that, reactor design is important. The designing is currently being done jointly by the JAEA and Mitsubishi Heavy Industries, a core company. At this moment, we think that somewhere around 200 to 300 will be appropriate, but that depends on where we place importance onto, output or volume of hydrogen manufacturing. If we prioritize hydrogen manufacturing volume, we may decide to leverage temperature by even dropping the output a little. This is still under study, therefore we would like to communicate about this after the decision is made. As for the budget, we have requested the budget for demonstration as part of the current GX, though I expect the budget for the first unit to be around 500 billion yen. Though we still have not completed an estimate, I suppose that we will be scrutinizing as to what would be the appropriate level of budget while referring to things such as joint development with the UK. What was the other question? What about commercial reactor? Oh, commercial reactor. As for commercial reactor, as I mentioned, we are proceeding with the evaluation on how many units of high-temperature gas-cooled reactor we should create at an energy center to be set up inside industrial complex. I suppose that to directly use up hydrogen without the loss would be the most ideal. Since the UK already has decided its location, I personally feel that the UK will do this earlier. So we can perhaps have it built in the UK first and show its effective aspect of it to the people to bring it back to Japan. I hope we can be at that stage in the first half of 2040s. Thank you for the question. Anyone here with any questions? If so, please raise your hand. We have another question from an online audience. Let me share it with everyone. In the beginning of the event, President of the JAEA mentioned that the key technology that links nuclear with renewables is uranium storage battery. How much progress have you made for its development? What is the timeline for commercialization? What is the difference of cost between that and other normal storage batteries? I, Sugawara, will explain. The uranium redox flow battery is still at stage of basic research, as I explained. At this moment, we are trying to conduct demonstration of principle by the end of this fiscal year. If that demonstration is successful, then our idea is to proceed with battery designing. If the demonstration is successful, we look forward to developing such storage batteries within the next few years, which I believe is to be in a very small scale. As for comparison of it against other storage batteries, I think there was an appendix on my presentation material. Excuse me. I think this serves as an explanation to that question. There are many different types of storage battery, out of which lithium-ion battery is quite popular. On the other hand, redox flow battery is excellent in terms of its large capacity. in terms of monitoring of recharge, status, and safety. We sometimes hear news about lithium-ion batteries exploding, but one feature of the redox flow battery is that such things do not occur. On the other hand, in terms of resource, as I said before, if we are to use vanadium, securing of resources can be quite challenging. But other than that, I feel that it relatively has good features. If we could replace the material with uranium, then, from the standpoint of securing resources, it can be an attractive storage battery. Thank you for the question. Are there anyone inside the venue with any questions? If not, let me share another question on high-temperature gas-cooled reactor from an online audience. I think the high-temperature gas-cooled reactor is fit for direct processing of spent fuel. But is development of reprocessing technologies necessary? Back end of fuel is being done in accordance with policies, which means we will work on reprocessing technologies as well. As I already mentioned, establishment of pre-processing technologies is necessary to be part of light water reactor cycle. We have done that with fresh fuel once, but we still have not done that with spent fuel. Development of the technology is a homework for the future. In other countries, direct processing is considered, but based on policies, we will be processed in Japan. Thank you. Due to set program, we will close Q&A session. Remaining questions from the audience here and online can be accepted through an email address dedicated for inquiries, which was shared with you beforehand. The deadline for submission is Tuesday, November 21st. We will post responses to your questions on our website. To close today's event, we would like to have Executive Vice President Itakura of the JAEA to make a closing remark. My name is Itakura. I am Executive Vice President of Japan Atomic Energy Agency. Thank you for participating physically or online in JAEA Annual Symposium. There are more than 200 participants who are present physically. There are more than 1,500 people participating online. I would like to show my appreciation once again for your participation. We decided to change the tone of annual symposium this year a bit. The theme of the event is Realization of Hydrogen Society. You cannot really tell that it really is a JAEA's annual symposium just by that theme, but as our president mentioned in his remark, we adopted the vision of exploration of a new future with the synergy of nuclear and renewable in April of this year. And the symposium is held in alignment with that vision. At today's symposium, we had Professor Kato talk about current situation corroborated by data along with future prospects. The JAEA also explained our initiative for realization of hydrogen society based on high-temperature gas-cooled reactor. In an area a bit different from hydrogen society, Currently, a lot of progress has been made with nuclear power-related innovation as well. For example, we are starting to see venture companies for batteries that utilize isotopes in the West. And much progress has been made with IoT technologies recently, and small amount of power needs to be supplied to the IoT sensors for a long period of time. We are starting to see companies that develop the long-lasting power supplies. The JAEA is looking forward to proceed with the diverse R&D activities mentioned by Sugawara to explore a variety of potential that nuclear power has. What we shared with you today are only at basic stage at this moment, but we look forward to steadily engaging in development for commercialization. We look forward to your continued support. There are some matters I would like to tell you in the end. You should be able to find a survey sheet or a section on our website where you can find a survey for today's symposium. Your feedback is very much appreciated. Furthermore, some special local products from municipalities where our facilities are located are on sale. The audience here is kindly asked to pay a visit there. Thank you for your participation in the symposium today. This brings us to the end of 18th JAEA Annual Symposium. We have a survey on today's symposium available on our website. The deadline for submission is Tuesday, 21st of November. Thank you for your cooperation in advance. We have provided a survey sheet as part of today's handout to audience here today. Please fill in the survey sheet. We will collect them as you leave this room. Thank you for your cooperation. Today's video will be available on our website as well. Once again, we would like to thank physical and online audience members for participating in the 18th JAEA Annual Symposium. Please allow us to thank the audience once again for so many of you participating physically or viewing the event online.